Chapter 9 of Introduction to Mathematical Philosophy by Bertrand Russell. This LibriVox recording is in the public domain. Infinite series and ordinals. An infinite series may be defined as a series of which the field is an infinite class. We have already had occasion to consider one kind of infinite series, namely progressions. In this chapter, we shall consider the subject more generally. The most noteworthy characteristic of an infinite series is that its serial number can be altered merely by rearranging its terms. In this respect, there is a certain oppositeness between cardinal and serial numbers. It is possible to keep the cardinal number of a reflexive class unchanged, in spite of adding terms to it. On the other hand, it is possible to change the serial number of a series without adding or taking away any terms, by mere rearrangement. At the same time, in the case of any infinite series, it is also possible, as with cardinals, to add terms without altering the serial number. Everything depends upon the way in which they are added. In order to make matters clear, it will be best to begin with examples. Let us consider various different kinds of series which can be made out of the inductive numbers, arranged on various plans. We start with the series 1, 2, 3, 4, and so on to n, and so on, which, as we have seen, represents the smallest of infinite serial numbers, the sort that Cantor calls omega. Let us proceed to thin out this series by repeatedly performing the operation of removing to the end the first even number that occurs. We thus obtain in succession the various series 1, 3, 4, 5, and so on to n, and so on to 2, 1, 3, 5, 6, and so on to n plus 1, and so on to 2, 4, 1, 3, 5, 7, and so on to n plus 2, and so on to 2, 4, 6, and so on. If we imagine this process carried on as long as possible, we finally reach the series 1, 3, 5, 7, and so on to 2n plus 1, and so on to 2, 4, 6, 8, and so on to 2n, and so on, in which we have first all the odd numbers and then all the even numbers. The serial numbers of these various series are omega plus 1, omega plus 2, omega plus 3, and so on to 2 omega. Each of these numbers is greater than any of its predecessors in the following sense. One serial number is said to be greater than another if any series having the first number contains a part having the second number, but no series having the second number contains a part having the first number. If we compare the two series 1, 2, 3, 4, and so on to n, and so on, 1, 3, 4, 5, and so on to n plus 1, and so on to 2, we see that the first is similar to the part of the second, which omits the last term, namely the number 2, but the second is not similar to any part of the first. This is obvious, but is easily demonstrated. Thus, the second series has a greater serial number than the first, according to the definition, that is, omega plus 1 is greater than omega. But if we add a term at the beginning of a progression instead of the end, we still have a progression. Thus, 1 plus omega is equal to omega. Thus, 1 plus omega is not equal to omega plus 1. This is a characteristic of relation arithmetic generally. If mu and nu are two relation numbers, the general rule is that mu plus nu is not equal to nu plus mu. The case of finite ordinals, in which there is equality, is quite exceptional. The series we finally reached just now consisted of first all the odd numbers and then all the even numbers, and its serial number is 2 omega. This number is greater than omega or omega plus n, where n is finite. It is to be observed that, in accordance with the general definition of order, each of these arrangements of integers is to be regarded as resulting from some definite relation, For example, the one which merely removes 2 to the end will be defined by the following relation: x and y are finite integers, and either y is 2 and x is not 2, or neither is 2 and x is less than y. The one which puts first all the odd numbers and then all the even ones will be defined by x and y are finite integers, and either x is odd and y is even, or x is less than y, and both are odd, or both are even. We shall not trouble, as a rule, to give these formulae in future, but the fact that they could be given is essential. The number which we have called 2w, the number of a series consisting of two progressions, is sometimes called the product of omega and 2. Multiplication, like addition, depends upon the order of the factors. A progression of couples gives a series such as x sub 1, y sub 1, x sub 2, y sub 2, x sub 3, y sub 3, and so on, to x sub n, y sub n, and so on, which is itself a progression. But a couple of progressions gives a series which is twice as long as a progression. It is therefore necessary to distinguish between 2w and the product of omega and 2. Usage is variable. We shall use 2w for a couple of progressions and the product of omega and 2 for a progression of couples. And this decision, of course, governs our general interpretation of the product of alpha and beta when alpha and beta are relation numbers. The product of alpha and beta will have to stand for a suitably constructed sum of alpha relations, each having beta terms. We can proceed indefinitely with the process of thinning out the inductive numbers. For example, we can place first the odd numbers, then their doubles, then the doubles of these, and so on. We thus obtain the series 1, 3, 5, 7, and so on, to 2, 6, 10, 14, and so on, to 4, 12, 20, 28, and so on, to 8, 24, 40, 56, and so on, of which the number is omega squared, since it is a progression of progressions. Any one of the progressions in this new series can of course be thinned out, as we thinned out our original progression. We can proceed to omega cubed, omega to the fourth power, and so on to omega to the omega power, and so on. However far we have gone, we can always go further. The series of all the ordinals that can be obtained in this way, that is, all that can be obtained by thinning out a progression, is itself longer than any series that can be obtained by rearranging the terms of a progression. This is not difficult to prove. The cardinal number of the class of such ordinals can be shown to be greater than Aleph sub 0. It is the number which Cantor calls Aleph sub 1. The ordinal number of the series of all ordinals that can be made out of an Aleph sub 0, taken in order of magnitude, is called omega sub 1. Thus, a series whose ordinal number is omega sub 1 has a field whose cardinal number is Aleph sub 1. We can proceed from omega sub 1 and alpha sub 1 to omega sub 2 and alpha sub 2 by a process exactly analogous to that by which we advanced from omega and Aleph sub 0 to omega sub 1 and Aleph sub 1. And there is nothing to prevent us from advancing indefinitely in this way to new cardinals and new ordinals. It is not known whether 2 to the Aleph sub null is equal to any of the cardinals in the series of Alephs. It is not even known whether it is comparable with them in magnitude. For aught we know, it may be neither equal to, nor greater, nor less than any one of the Alephs. This question is connected with the multiplicative axiom, of which we shall treat later. All the series we have been considering so far in this chapter have been what is called well-ordered. A well-ordered series is one which has a beginning and has consecutive terms, and has a term next after any selection of its terms, provided there are any terms after the selection. This excludes, on the one hand, compact series, in which there are terms between any two, and on the other hand, series which have no beginning, or in which there are subordinate parts having no beginning. The series of negative integers in order of magnitude having no beginning but ending with -1 is not well ordered, but taken in the reverse order, beginning with -1, it is well ordered, being in fact a progression. The definition is: a well-ordered series is one in which every subclass, except of course the null class, has a first term. An ordinal number means the relation number of a well-ordered series. It is thus a species of serial number. Among well-ordered series, a generalized form of mathematical induction applies. A property may be said to be transfinitely hereditary if, when it belongs to a certain selection of the terms in a series, it belongs to their immediate successor, provided they have one. In a well-ordered series, a transfinitely hereditary property belonging to the first term of the series belongs to the whole series. This makes it possible to prove many propositions concerning well-ordered series which are not true of all series. It is easy to arrange the inductive numbers in series which are not well ordered, and even to arrange them in compact series. For example, we can adopt the following plan. Consider the decimals from 1/10 inclusive to 1 exclusive, arranged in order of magnitude. These form a compact series. Between any two, there are always an infinite number of others. Now omit the dot at the beginning of each, and we have a compact series consisting of all finite integers, except such as divide by 10. If we wish to include those that divide by 10, there is no difficulty. Instead of starting with 1/10, we will include all decimals less than 1, but when we remove the dot, we will transfer to the right any zeros that occur at the beginning of our decimal. Omitting these, and returning to the ones that have no zeros at the beginning, we can state the rule for the arrangement of our integers as follows. Of two integers that do not begin with the same digit, the one that begins with the smaller digit comes first. Of two that do begin with the same digit, but differ at the second digit, the one with the smaller digit comes first, but first of all the one with no second digit, and so on. Generally, if two integers agree as regards the first n digits, but not as regards the n+1th, that one comes first which has either no n+1th digit or a smaller one than the other. This rule of arrangement, as the reader can easily convince himself, gives rise to a compact series containing all the integers not divisible by 10. And, as we saw, there is no difficulty about including those that are divisible by 10. It follows from this example that it is possible to construct compact series having Aleph null terms. In fact, we have already seen that there are Aleph null ratios, and ratios in order of magnitude form a compact series. Thus, we have here another example. We shall resume this topic in the next chapter. Of the usual formal laws of addition, multiplication, and exponentiation, all are obeyed by transfinite cardinals, but only some are obeyed by transfinite ordinals, and those that are obeyed by them are obeyed by all relation numbers. By the usual formal laws, we mean the following. 1. The commutative law. Alpha plus beta is equal to beta plus alpha, and the product of alpha and beta is equal to the product of beta and alpha. 2. The associative law. The sum of alpha and beta with gamma is equal to the sum of alpha with the sum of beta and gamma, and the product of alpha and beta with gamma is equal to the product of alpha with the product of beta and gamma. 3. The distributive law. The product of alpha with the sum of beta and gamma is equal to the sum of the product of alpha and beta with the product of alpha and gamma. When the commutative law does not hold, the above form of the distributive law must be distinguished from the product of the sum of beta and gamma with alpha is equal to the sum of the product of beta and alpha with the product of gamma and alpha. As we shall see immediately, one form may be true and the other false. 4. The laws of exponentiation. The product of alpha to the beta power with alpha to the gamma power is equal to alpha raised to the sum of beta and gamma power. The product of alpha to the gamma power with beta to the gamma power is equal to the product of alpha and beta raised to the gamma power, and alpha raised to the beta power raised to the gamma power is equal to alpha raised to the product of beta and gamma power. All these laws hold for cardinals, whether finite or infinite, and for finite ordinals. But when we come to infinite ordinals, or indeed to relation numbers in general, some hold and some do not. The commutative law does not hold. The associative law does hold. The distributive law, adopting the convention we have adopted above as regards the order of the factors in a product, holds in the form the sum of beta and gamma taken as the product with alpha is equal to the sum of the product of beta and alpha with the product of gamma and alpha, but not in the form the product of alpha with the sum of beta and gamma is equal to the sum of the product of alpha and beta and of gamma and alpha. The exponential laws, alpha raised to the beta power taken as the product with alpha raised to the gamma power is equal to alpha raised to the beta plus gamma power, and alpha raised to the beta power raised to the gamma power is equal to alpha raised to the product of beta and gamma, still hold, but not the law alpha raised to the gamma power taken as the product with beta raised to the gamma power is equal to the product of alpha and beta raised to the gamma power, which is obviously connected with the commutative law for multiplication. The definitions of multiplication and exponentiation that are assumed in the above propositions are somewhat complicated. The reader who wishes to know what they are and how the above laws are proved must consult the second volume of Principia Mathematica, starred numbers 172 to 176. Ordinal transfinite arithmetic was developed by Cantor at an earlier stage than cardinal transfinite arithmetic, because it has various technical mathematical uses, which led him to it. But from the point of view of the philosophy of mathematics, it is less important and less fundamental than the theory of transfinite cardinals. Cardinals are essentially simpler than ordinals, and it is a curious historical accident that they first appeared as an abstraction from the latter, and only gradually came to be studied on their own account. This does not apply to Frege's work, in which cardinals, finite and transfinite, were treated in complete independence of ordinals. But it was Cantor's work that made the world aware of the subject, while Frege's remained almost unknown, probably in the main on account of the difficulty of his symbolism. And mathematicians, like other people, have more difficulty in understanding and using notions which are comparatively simple in the logical sense than in manipulating more complex notions which are more akin to their ordinary practice. For these reasons, it was only gradually that the true importance of cardinals in mathematical philosophy was recognized. The importance of ordinals, though by no means small, is distinctly less than that of cardinals, and is very largely merged in that of the more general conception of relation numbers. End of chapter 9.